So just a bit of background. So as you can tell from my accent already, I'm British, and I moved across to Silicon Valley last year in March. And the background is I was the main author of the data.table package in R, and the main thing that does is it doesn't use hash tables. It scales up by using fast radix sorting. But the problem with that is it's single-threaded and it's single node. So I saw H2O present at one of the R conferences, and they presented and said that, well, they've already made a data frame distributed and massively parallel. So I thought, well, this seems to be an ideal environment to scale up the data table algorithm. And it's just been an experiment to see how far we can go. So the presentation's all online, and there's very little slides. So I'm connected over VPN, over the Wi-Fi here at Galvanize to the H2O office, and you're looking at our 10 physical node cluster. So the windows in the middle are 10 256 gig RAM 32 core machines. So we have 320 cores in total. These bars here are the IF top that's running on each of the boxes to see the network traffic going between each of the boxes. And these columns here are small numbers, so just for my benefit really, the first number is the amount of RAM I'm using on this box, and the second number is the amount of RAM everybody else in the firm is using on this box. So I've asked everyone in the company back in Mountain View just to hold off using these servers while I'm doing this demo now. So what we're going to do, we're just going to do some joins in parallel and distributed. So first of all, let's start up H2O. So if we just log on to one of these boxes, I've got some aliases set up. Let's make this a bit bigger. Just shout if you can't read this. So if I have a look at an alias of SSH1, it's just an SSH with -x to machine number 1. So conveniently, the machines are just called machine 1 to 10. So if we log on to that guy and have a look at the files there, there's H2O. It's just a jar file. That's it. Everything's contained in one file. You can download that from our website, or it comes as part of the H2O R package, or it's part of the Python H2O package. And you just download it and then stick it onto each of the servers. And essentially all you have to do is Java -class path of h2o.jar. Tell it how much memory if you want, but that's essentially it. And when you start that on this server, it'll send a broadcast message with this name that you provide to it. So we'll say mattd 42 just to make a unique name. And as long as you give the same name to the other JVMs on the other boxes, they'll broadcast to each other and then hook up with each other. You don't need to set any environment variables in advance to make the cluster talk to each other. So rather than do that on all 10 machines and copy and paste a command like that, I've already got an alias set up, and the alias takes an argument, an environment variable, which is hosts. So these are 10 machines. Let's have a look at the start cluster command, and it's just a for loop, and it's for loop in the hosts, start SSH and start Java, passing it the Java command. So you can start H2O with a yarn environment and other GUI environments as well. It's just that I'm doing it manually because I'm a hacker, in quotes, and so I like to control the arguments and know what's going on and not have a layer between Java and yarn, whatever yarn's doing. So I'm just going to type SCL, and that's sending the command off to start Java on each of the boxes. Hopefully it'll come back with a message saying it started the cluster OK on the 10 machines. Is the text big enough at the? Can you read that? SCL. Now we've got You can do this from R, or you can do it from Python. I'm just using R because I know it better, but it's just the same in Python. And the way I do it is just with gedit, and it sends, F5 just sends the command to the last window. So if I click that one, and then click this one, and then click here, and then press F5, it sends R and starts R. So I like doing this because I can send Unix commands, which I do quite a bit, Python, or R, or Scala, or whatever's running at the bash prompt, I can just send with one keystroke. So R started. Now let's start H2O, so there's a library loaded, and let's connect to the cluster. We can connect to any one of them. There isn't a main node like a driver node. There's no name node in H2O, so we can choose any one. Let's just choose machine number 2, and 55666 was set up in that alias, so that's my port number that I just chose. So we're connected to Mr. 2. We've got 320 cores, we've got 10 nodes, and we've got 2 gig in this cluster. Sorry, not 2 gig, 2 terabytes. So let's load from HDFS. So let's load up 1 billion rows. So that's just this command, h2o.import file, and you just pass it the HDFS file path to the file. So let's put this in the background so we can see it working. So we've got the 10 nodes loading the file in parallel from HDFS. And I've moved the windows around here so that to put this bash prompt at the top of the screen so you can see it from the back. So the machine 6 here is the one that's really active, and that's because that's the HDFS name node, and it seems that data's flowing in through the name node. And so it seems a bit strange to me that this is how HDFS works. And there's mapr as well, which doesn't have a name node. So that's an alternative. But it would be nicer if the data was stored in some fashion where H2O could know where it was locally and just load it up locally on each node. Anyway, that's finished. That's 1 billion rows and loaded up. What did we name that symbol? We named it X. So let's have a look at X. So it comes back instantly. It just shows the top 6 rows. So it's just 2 columns, and it's random integers sampled between 1 and 1 billion. And the key is this, so that's the key, and we've just got some random data in X, positives and negatives. And this is about 20 gig, something like that. So let's load up a second file of 1 billion rows. So that's going to be the same format, same key and random data, randomly sampled between 1 and 1 billion. So it's a very high cardinality test. So you've got lots of unique keys. Most of the keys just occur once, some twice, some 3 times, depending on how the uniform distribution has picked those numbers. Let's just put that to the background so we can see the clusters. We've got a bit of latency there, probably because of the Wi-Fi, and it's finished. Okay, so let's look at Y. So Y is another table, 1 billion rows, and let's join them. So it's just, how many R users are there? Okay, good, a few. Python users? About the same. Other people SQL? Good, everyone knows SQL. So the base syntax, similar to Python, similar to Pandas. And so we've just got h2o.merge, the left table, the right table. And in this case, the method radix is this new method I'm showing. It's in test, so you need to pass method equals radix. So let's just run that. That comes back instantly because it's lazy. So we need to do something with it. Let's just print the dimension of the answer. So it's running now, and we can see it. See all the cores are busy, And we can see the data is being transferred between the nodes at the same time. So want to use, when I'm performance tuning this, I want to use the network and the CPUs at the same time as much as possible. I don't want to just use CPUs and then the network, CPUs, then the network. So it's proceeded through, it's finished, I think. Yep, so it took 22 seconds to join that very high cardinality 2 tables together. And let's have a look at the result. Just look at the top rows. So we've seen that key 0 was picked 3 times in the left table, as it happens, and once in the right table. So we see that the right table value has been repeated 3 times to match with the 3 values in the left. Key value number 2 only occurred once in the left and the right, so just 1 row comes back in the result. Key value 1 wasn't picked in both tables. Yep.
All right, I have a dumb question. I'm riveted by this, but you say the blue and then on the left, where's the network I/O and where is the CPU?
Ah, sorry. So these middle blocks, blue means idle.
Yeah.
Those are CPUs.
Yeah.
Green means user time. Red means system time. So all these middle blocks are just CPU. And then these boxes over here, this. Every time you see a white bar going across horizontally, that's network traffic.
So there are multiple network interfaces on each of those nodes, because there are several white bars.
Yes. So these are all the pairs. So here it's showing you this machine number 7. It's sorted like it's like top, but for it's IF top. Okay. So it's the most active pairs that machine 7 is talking to. So machine 7 will be talking to 9 other machines.
One network interface on each node then?
Yes, I think so. Yeah. They're all in one rack with one switch at the top. Okay. Yeah. And so that's that. So that joins run. And let's have a look at the bottom. So we can look at the last few rows. Now, if anybody knows how to do that in Spark, Scala, just give me the last 3 rows. Please just let me know, because I've tried, and I can't do the same as tail. Sorry?
It's take right.
Take.
Take right if it's sequence, or there's a function take right with a number of elements.
Take. I've seen take.
Yes,
and
take is from
take.
the pair, but
take.
Right is from the right.
One word. Take right.
Yes.
One take right. Okay, I'll look at that. Thank you. And then what else can we do? So this is just like an R data frame. So it's ordered in memory across the 10 nodes. So we can look at let's have a look at the 500 millionth row. 1, 2, 3, 1, 2, 3. Oh, got the wrong name. So answer 1. So that should come back with 1 row pretty quickly. You've got the key value is pretty much in the middle between 1 and 1 billion. And then you've got the 2 data values from the left and the right. So, so you can do left outer join, inner join, all the usual things you can do with joins. So let's scale up. That was only really 1 billion. 1 billion you can do on a single node, right? It's 32-bit addressability. We could do this 1 billion join could happen on 1 node. So let's just go ahead and generate 10 billion row tables. Now, just to speed things up, rather than loading from HDFS, it'll be loading 200 gig on the left, 200 gig on the right, and then creating, because it's 3 columns in the result, that would be 300 gig result. So we're going to create 700 gigs of RAM in this test. So it's going to take quite a while. So let's just create some random data using a random creation function that we have in H2O. You just give it the number of rows, the number of columns, and the fraction of different types of columns. So here we're just going to say just 2 columns between 1 and 10 billion. And let's just go. So let's move it down so we can see it happening. So it started, 3% done. Let's just watch the system as it's creating. So it's the way that this is just creating random data, so it doesn't really need to be fast. So it's single-threaded on each of the nodes, but each of the nodes is happening separately. And the first time I did this, I did create a 200 gig file on HDFS, and I used awk in the same way that I'd done it for the smaller sized files. And the join worked, and it returned the data, but it returned 50 billion rows as a result, which isn't what I was expecting. I was expecting just over 10 billion. So I looked into it and looked at the algorithm and the way it was working and the way it was supposed to work, all kinds of bugs that could have been. And it's quite difficult to debug a large data problem like that because every time you do a query, each of those queries takes some time itself. So eventually it came down to the fact that it was actually doing the right thing and the result was correct. And the input data wasn't selecting enough random keys. And the randomization algorithm in awk didn't have a great enough period. So it reached a 1 billion period and started to repeat its random number generation. So it wasn't picking all the numbers between 1 and 10 billion. So I changed, and what we use in H2O already, but I didn't know until this point, was the this PCG random number generators. So this is what H2O uses, and I just hooked it up with their C level. They've got a GitHub, and you can download the C code. And I just hooked that up to be able to generate these 10 billion row files with good randomness, and then that worked and returned the 10 billion row result. So that's a good website if you need it. Okay, so where are we now? So we're almost 96% done on creating the 10 billion rows. So there's X, so we've got, let's just make sure. So we've got 1, 2, 3, 1, 2, 3, 1, 2, 3, yep. So we've got, now the way this function is creating random keys between minus 10 billion and plus 10 billion. So let's just leave it like that for the moment. We can have negatives in the keys if we want, so that's fine. And to tidy up, just to make it easier, let's just change the column names to be key and X1. So we've done that, it does it by reference. Have a look again at the data. So there's our, let's just make sure that the column names have changed to be the key and the X1. Right, so let's go ahead and create the, oops. Is that running, hopefully? Right, that's creating the second table. So while that second table runs, let's cross our fingers. There's, let's go just through a few slides. So just a reminder that H2O is completely open source, developed in the open. The GitHub page is there, and you see us committing to it in real time. Always will be open source. And just to reiterate where this true radix sorting comes from these two articles we got the idea originally on how to sort differently and how we can sort floating point data. And we extended this. Their articles sort radix backwards, but we're going forwards. And that's been included in R itself to make ours sorting much faster. In the last few weeks, that's been released. But it's single-threaded, single node, and limited to 2 billion rows in data table. So that's been parallelized in H2O. The data table join works by finding the order of the left columns, finding the order of the right columns. That ordering is the index. So no matter how many columns you have in your index, this index is always the same size because it's just the ordering vector. So no matter, you can have 10 columns in your index, it's going to be the same size. And then because they're ordered, it makes the binary merge much easier. And because there's no hash table at all and we've got this ordering, it provides some extra features that we can't really do with hash tables as easily. And we can roll forwards, backwards to the nearest observation, and we can limit staleness. So say you've got some time series, you've got irregular data, tick data, Internet of Things, device data, and you want to say what was the temperature of the brakes of a particular car at 3 o'clock this afternoon, or the nearest observation to 3 o'clock, because there was no observation at 3 o'clock. It just goes straight. A SQL join would join to an NA because there's a missing observation, but because you've got an ordered index, then the prevailing observation before that missing value is easy to return. And we can say, well, give us the prevailing observation provided it was recorded within an hour of 3 o'clock. If it was 6 weeks ago, then I don't want to have stale information come back. And that's built into the join itself. You don't need to expand your data with NAs and then fill your NAs afterwards, because that's creating more data in RAM, which you then need to fill forward, and it's churning through RAM. So this approach builds it into the algorithm. Cardinality, of course, it's not just the number of rows that's in the data, but what's in those rows. So I'd say stock tickers, they're low cardinality, 500 is a small number. Millions of people, medium cardinality, and billions of devices, high cardinality. So one of the use cases is you've got several terabytes of new data a day. You need to ingest that, join it to another couple of terabytes, and decide what to keep before the next day starts. That's the awk script I described, which was fine up to 1 billion rows, but doesn't work for 10 billion. And then just to show the data, so as we're increasing the number of rows from 1 million up, we're also increasing the width of the key, which is really important for a decent test. So 100 million rows, 1 billion rows, the keys are getting wider, 10 billion rows, 200 gig. And then the H2O commands are really simple. You just library H2O or import H2O in Python. You init to the cluster, one command to load the data, and then merge just like R or Python, and then usual commands. So it's so simple it fits on one slide. And then the scaling, so I've just demoed the 30 seconds, actually came back as 20 seconds, didn't it, in that test. That was 1 billion rows, and we're just about to do the 10 billion rows. It should take about 10 minutes if it works. And then I've demoed this in the past, but only up to 1 billion rows. And so there's a YouTube video of the join working on 1 billion, which is on that link. So let's, hopefully the data's loaded. Yep. Sorry, not loaded, but being generated. Let's just check. Yeah, it's got the default names. Let's change the names. Okay. So we've got our X and Y, we've got 10 billion rows in each one. Each is about 200 gig, and we're going to create a 300 gig result. So that's started. Now, 10 minutes left. Perfect timing. So let's log on to that Mr. 2 machine. And there's a log file that's being generated, so let's have a look at that as it's running. So it's, let's make it a bit bigger. So you can see the CPUs are all happy and busy. Nothing happening on the network at the moment. So it started. So first thing it does is it creates a left index. So basically it's just sorting the table. So first thing it does is it does a histogramming of the most significant byte in parallel and distributed across the whole table. So then it knows how much of each bucket there is, and then it can work out the offsets, and it can send those subsets of data to the right node. So essentially, if you've got, think of it like a dictionary where you've got surnames or words from A to Z. It's putting all the words that begin with A on the first node, all the letters with B on the second node, and so on and so forth. And then once that data's there, with a row pointer to where the original data is, it then sorts locally on each bin, which is quite different to other algorithms, because other algorithms and other frameworks, they sort locally first and then do a merge afterwards. And that merge afterwards step is serial, right? This is a different approach, as far as I know. So it's already done all that splitting, so it's finished now, and it's finished the left index in 116 seconds, so just under 2 minutes. And that's really high cardinality, 10 billion rows. And now it's doing the right index. So it's doing the same thing. It's split up. It's counted the bins by the most significant byte. Now it's sending them to the right nodes. It's done that. And now it's on each node, it's sorting all those sub-pieces. So this is my day. Welcome to my development day of trying something new and then testing it and seeing if it works.
I'm an outsider from R, so I'll admit that right off. Thank you for H2O, but I don't know much about it. When I tried a few tricks in R to explore, I found that the memory expansion per variable was very large. That was my untrained observation, was that it was, so when I loaded a billion rows of CSV with different kinds of values to R, the amount of RAM that was taken seemed crazy to me.
Which function did you use?
I don't remember. So are we in a day when RAM matters so little because you can put this together?
No. So first of all,
Could you sum up the question for recording?
for the recording, yeah. So the question was,
RAM expansion on variables
so
in R.
the questioner admits you don't know R that well.
Correct.
And your initial first observations were that when you loaded data, R just consumed RAM very rapidly.
Yes.
It was a CSV file, wasn't it?
Yes.
So you probably used read.csv,
Okay.
which is the base R function to read.csv, which is appalling.
Okay.
Everyone knows that it's appalling. It's been appalling for a long time. So you just cannot use it.
Got it.
And there's no way, even if you pass all the arguments you're supposed to do, like if you tell it the number of rows in advance, if you know that from WC minus L or something from the command line, then it can get faster And there's some more tricks that can make it about 3 times faster. But even that's still appalling, because you're absolutely right, it does eat up RAM. So the fastest way is fread in the data table package, and that reads it much, much faster. So if you just use that. And I'm biased because I wrote that. So that's why one of the reasons data table is popular, because about 3 or 4 years ago, fread was added.
What's the relationship of H2O to data table?
Very little.
Very little.
So H2O is implemented in Java. So this is the JVM that you're seeing, which is being distributed and parallelized. So we're using all that great stuff with the garbage collector in Java, all those parallel threaded libraries and tools. And we're using R as a front end. So when you type R and it's a H2O frame, the computation gets sent to the back end, much like a database. And the same for Python. So we're using the same, so that all this is happening in Java land.
Thank you.
Yeah.
So speaking of Java,
So just while we're on the same topic, and then so H2O has H2O.import file, which is at least 10 times faster than fread that I wrote in data table, because data table's fread is single threaded on a single machine, whereas H2O.import file takes a CSV file, like from HDFS, these ones that we're reading now, or from local disk, and it'll read them in parallel on a single machine using all the cores and distributed across 320 cores. So that's why companies like PayPal are using H2O, because they tested fread versus H2O import file, and then this is just much faster. And it's why I'm at H2O, because I couldn't beat it.
So yeah, speaking of Java, at some point I thought that Cliff was working on a hacked version of the JVM, so what happened to that?
Not a hacked version of the JVM, but
specifically optimized,
yeah. So a lot of the things Cliff has, so this frame here, which is distributed and parallelized, is all Cliff's work mainly. So he designed the H2O frame, all the compression. So when H2O import file looks at the file, it's already got the data row by row, right? And it's very simple. It just maintains the minimum and maximum of the column that it's seen so far, and that's free to compute and maintain. So things like those optimizations he's put in.
Yeah, understood. Let me try to ask it a different way. The
Yeah.
JVM that you're using right now
Yeah.
is the stock JVM that
Yeah.
came with your Ubuntu.
No, it's the Oracle
Or
stock.
whatever, but it's a stock JVM.
Stock JVM, yeah.
So you guys didn't have a specialized version of the JVM?
No.
did you?
No.
Okay.
No, you can see it, yeah.
So all of the optimizations are just at the level of Java? Because that
Yes.
wasn't my understanding, but now you...
Well, Cliff may have put some optimizations into Java itself, because he can, I believe.
Yeah.
He would have done that years ago.
That was his FOSDEM presentation, you know, that he actually went all the way to the garbage collection implementation of OpenJDK and stuff like that. So to me, it meant that it would require a separate, copy of Java.
No, I think he was talking about what he's done in the past in the Java hotspot compiler, so, which is already in Oracle.
Okay, could be. And another question, what happens if the node goes down?
Good question. And what I like about it, the question is, what happens if a node goes down? Well, in my experience, this is a physical node in a rack, which I think companies are quite often likely to have. And nodes don't really go down. What happens is Java crashes. At this scale, 10.
That's actually my follow-up question, because the node could go down not just because of the hardware, because there I would absolutely agree with you. Software bugs typically.
Yes, software things. And I've seen Spark going down with Java, restarting and so on. It doesn't happen with H2O.
Okay.
Because it's just written, that doesn't happen.
Okay.
So I think there's a penalty of the resiliency in Spark that we're not paying. So if you run this disjoin in Spark, you'll see it writing to disk into the work directory, right? And it writes a lot so that it can recover if a node does go down. We just aim that the nodes don't go down, and we don't pay that cost. So it's a lot faster because it's truly in memory only.
Okay.
And we like that. So we're not really aiming for Yahoo scale or Google scale of thousands of nodes where cosmic rays can take down a cluster apparently. That's not really our space.
Okay, so and I totally respect your engineering choices.
that's fine to make that choice. Again, there's nothing wrong with it. But just sort of this obsession about hardware failures, that's not what the problem is, right?
Mm-hmm.
So I used to be on the original Hadoop team at Yahoo. Part of the reason it was engineered for extreme fault tolerance is because of software bugs. And all would go down because of the implementation itself being buggy.
Yes.
All the hardware going down.
Yes. Well, repeating it isn't going to make it not buggy anymore. It's still going to fail.
Recovery helps because then we can recover into a state that actually doesn't trigger a bug anymore.
It's in practice. It's very, very hard, though.
Finish, and then we can talk about it later.
No, that's a good point. But I think in my experience, when I've experienced those crashes, software bugs, Spark will repeat it over and over again, and it won't recover. That's what happens here, anyway. So that's has it finished? It might have finished. Yes. So that's 10 minutes. And let's have a look at the result. So that's, so remember it was randomly keys sampled between minus 10 billion and plus 10 billion. So the smallest keys are first. And it's ordered as well. So we didn't have to do a join then order by because part of the algorithm itself joins. And part of the process of that joining, remember we created that index and then we used it, and we created the second index and then we used it. We've still got those hanging around. So if we go and do a query and filter or join along those dimensions of the key, then it'll be much faster because those are knocking around, which is exactly the same as what we do in datatable in the R project. So what can we do now? Well, why don't we go and select the it's an ordered table, remember? So we don't have to do any kind of SQL adding a column which contains the row numbers or anything like that. We can just go ahead and select the 3 billionth row. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And type the right object name. So that should hopefully just come back.
So what's the performance of that expression? See, it didn't come back immediately. That's interesting.
Well, let's have a look.
To find the 3 billionth row, what's the performance there?
Yeah, that was a bit, that may be the Wi-Fi. Let's do it again.
Well, it's more up and down.
It's warm, right. So I can have a look at that. That could be...
I'm just curious.
I'm too, yeah. It would be nice to have that coming back instantly. And let's see. Yep, that's all I had.
I have a question.
Yep.
Actually, I have two questions. What you showed is good and it works, and I'm sure that's not one that it works, but what would you use it for? Could you give a use case?
Right, so, well, to be honest, part of it is sorry? Oh, to repeat the question. The question is, it's great, it works, it's amazing, but what would you use it for? So part of it is that this is the most difficult test we can think of to test the H2O infrastructure. So we've got a high cardinality test and so on. So you saw that the index was being created quickly. It was only took a minute or two to create the left index and the right index. So you can see immediately how that can be useful, is that faster. Building an index in a database is standard. You want to group faster, select faster. Often it's common. The key is often used and reused many, many times, as you don't want to do a vector scan over and over again. And this is just a way to test that it's doing the correct index, and then we're getting the correct result. But also, if you really want to join two large tables like this, one use case is, like I said, where you have several terabytes of new data each day, and you want to join them together quickly. And traditional databases are taking hours or possibly days, and you have to scale out and you have to all kinds of tricks. Scale out much more than we're using here. many more than 10 machines to get them to compute the result within one night before the next day starts. Anything with Internet of Things, with devices, very high cardinality. People are using it for unique product codes because they are integers. Of course, we can do non-integers as well, strings and enumerations, but quite a lot of data does actually have these very large integer numbers which need to be joined together. Devices in cars, like progressive, all the GPS data and all the car telemetry that's coming off these devices are pouring in every day. That has to be ingested, sorted, features calculated each night and stored before the next day starts.
Thank you very much, Matt.
Great, thank you.